Welcome to the Simons program at the Niels Bohr International Academy in 2016. In the next 1.5 hours, you will hear a lecture by one of the masters of theoretical physics today. His name is Alexander Polyakov and he is professor at Princeton University. Professor Polyakov has ranged his work from statistical mechanics, quantum field theory, and as you will hear today, turbulence, the field of fluid dynamics. This looks like they're completely disparate subjects, but in fact, they're not. And Polyakov's approach to physics is precisely the unity of physics. He understands structures that go from the deepest of quantum field theory to systems in condensed matter physics, statistical mechanics, and as we will see also in the classical problem and still unsolved problem of turbulence in fluid dynamics. When he goes to the blackboard and gives his lectures, there's silence in the auditorium. People want to know every word that's coming out. As you will see, he's nevertheless also an easygoing character and he can also joke about the subject. So people stay awake and they go away with the feeling that they have really felt and met someone who has a deep insight and who is able to convey it to others.
My plan is to speak about, some applications of methods of fundamental physics which developed in the last decades or so to some classical problem. Actually, the theory of it is very strange and ironic that we still don't have the theory of turbulence, because in the Kolmogorov form it inspired actually a lot of things. For example, the theory of critical phenomena, which is in a relatively good shape, not perfect, but relatively good shape, it was definitely the idea of scale invariance and generalization group. Definitely comes from, well, I know for sure that it came from analogies with hydrodynamics. The intermittency, which Jeroen spoke about, it appeared in particle physics when you have, for example, if you have E plus or minus annihilation, it produces a photon. It's a plus or minus, a virtual photon, and then a lot of stuff. That's the amplitude, and you select, you have two things. You have initial energy of a plus or minus and energy of one of the particle. And then you have a probability distribution for the function of two variables. Turns out that if you calculate the nth moment with this thing, it's energy to the power gamma of n, some anomalous dimension, and now in QCD we know explicitly the answer for this. Moreover, the physical picture is the cascade. You produce heavy jets which begin to decay. This is analogy with Kolmogorov, Richardson, etc. But the difference between the status of this theory and Kolmogorov theory is roughly that, and turbulence theory is roughly that this theory is more or less complete. We know explicit expressions for gamma. We know we're more or less able to answer all we want, all questions we want to ask here. While in turbulence we're still in the Stone Age. It is still a huge field, which is in a sense, the situation is in a sense opposite to the fundamental physics, because in fundamental physics we have a lot of tremendously powerful apparatus and very few experiments, unfortunately. In turbulence, it's the other way around. There are plenty of numerical and wind tunnel experiments, but very little of the theoretical understanding. It seems that having in mind both fields is useful, and that's what I will be trying to do, to draw some analogies. And please also interrupt me anytime. It would be very useful, for otherwise the talk will become confusing. And for me it will be also very useful if you interrupt me with questions. Okay, but that's probably self-obvious. Okay, so what do we have in turbulence? It is, as we already discussed here, when we have statistical mechanics, it's the theory of microcanonical distribution, of the Gibbs distribution. You derive the general statistics for any system having fixed energy, and you know the probability, and then you know the probability distribution, which is the Gibbs-Boltzmann probability distribution, and all that remains, which is not to say it's easy, but all that remains is to calculate the averages with a given probability distribution. In the theory of turbulence, the problem is twice as hard, because not only we don't know how to calculate expectation values, we don't know what the probability distribution is. And I remind you, Jeroen already mentioned this, that we have the interesting domain to study theoretical turbulence is to look at the so-called inertial interval. The inertial interval is we have some source of energy which excites turbulence and generates some large fluctuations, then which has the size L. Then we have the decay, the cascading process. You see the analogy with this. And finally, when the perturbations become small, viscosity stops them. Viscosity is the ultraviolet cutoff in this theory. And which happens at some range A, so that the inertial range is the intermediate range where dissipation is negligible, and we also don't feel directly the details. We can hope for universality, that the physics here will be independent on how precisely you generated these original large fluctuations. Which is so that is about the eraser. Oh no, I don't. On the right. Oh, that's the. Yeah. I couldn't believe this is the eraser. Anyway. So, how one approaches to this theory, to build a theory. So let me just say I will spend a few minutes to explain the well-known things, just to set the stage. So we have the Navier-Stokes equation. And F is a random force. And as I said, turbulence can be perceived as a spontaneous symmetry breaking in the sense that spontaneous symmetry breaking in statistical physics is the reaction to infinitesimal fields. Infinitesimal magnetic field in some direction will cause magnetization in this direction. Here we have the analog of magnetic field is this random force. If you have, it is statistical by hand. It's made fluctuating by hand, it's random. But then we, in a sense, remove it. And then for laminar phase, the randomness will disappear, while in the turbulent phase, the randomness will remain. And to describe this,
what do you mean it will remain? It will propagate to small scales and will be ultimately damped. So if you remove the forcing, nothing happens.
That's right, but if you have the forcing and you have a dissipation, then you are in thermal equilibrium, then you start removing these. You will get, of course, you have to supply energy and you have to supply dissipation, but the absolute value of both things are irrelevant. As I said, nu plays the role of ultraviolet cutoff, and indeed there is the analogy we send nu to zero, and we ask the question whether dissipation remains. So we basically asking the question where nu tending to zero is the same or not the same as nu equal to zero. Whether with the Navier-Stokes equation will go to the Euler equation in this limit or not. Actually, it's very well known that even without turbulence, if you take viscosity to zero, if viscosity is zero, then there are solutions of the type of zigzags of multi-valued velocities. They turn into the shock waves. The basic reason is that in the shock wave, so you have the profile of velocity like that in one dimension, and you have to use the Maxwell rule, so the physical distribution of velocity is like that, and that is the shock wave. And the reason why this limit, this limit is very subtle, is that the gradient inside the shock waves are so large that they compensate the smallness of nu. So inverse nu, as I said, is the ultraviolet cutoff. And let me give you an analogy. Namely, we know that if you have quantum electrodynamics, we have axial current, which is conserved for massless theory classically, and we know following Schwinger and Adler and Bell and Jekieff that if you regulate the theory, to regulate the theory, you need the point splitting. So you have to examine things like that. And the divergence of this thing will be, in quantum electrodynamics, will be just I call it J mu 5 of x and y. And you classically, as y goes to zero, you get zero, but we know from the singularities of this thing that the divergence of this thing will tend to FF dual, the famous result. Now let's do the same thing for turbulence and see what happens. One thing which I will need in a minute from now is that this coefficient here is, well, I withdraw this phrase. I will come back to this a little later, but I just wanted to explain the momentum space topology of the anomaly, but we probably don't have time for that. So let's do something similar for hydrodynamics. There are many different forms. One of the I will do it in the very in a very simple case. Let's take 2D turbulence. Actually, I forgot to say that my plan is to discuss some general features of turbulence and analogies, but also at the end I hope to show you some new result for the correlation function, which is non-trivial. It may be so non-trivial that it is even incorrect. But in any case, we will discuss something new at the end. So far, it's old stuff, which is not very well known, though. Okay, so let's the new result which I promised to provide you is refers to 2D turbulence, and in the 2D case we have the object called vorticity, which is just epsilon alpha beta d alpha v beta, and I'm going to derive the an anomaly equation for this guy. It satisfies the equation omega dot if we neglect viscosity and forcing. Suppose we are in the region where we are in the inertial range where in which viscosity and forcing are irrelevant, and so we have this equation, and it has infinite number of conserved integrals. In particular, it has the important integral for us will be what is called entropy, which is omega square of x. Well, locally entropy is 1/2 omega square of x. Now let's do the point splitting once again. If we want, we can discuss the entropy or any other integrals of motion when you have no point splitting, but explicit presence of the ultraviolet cutoff. That's one thing, but that's correct, but actually not very useful. Instead, we do the point splitting and look at this, at how this point splitted integral of motion actually behaves. To explain why it is what it really means, it's useful to go to the momentum space. In the momentum space, entropy itself is sum over all possible momenta, omega k, omega minus k. But when the point splitting is equivalent to saying that k is less than lambda, which is of the order of 1/y. That's the standard stuff in quantum field theory. So let's look at this, and excuse me. And we expect that we have a cascade with dissipation of entropy, so that we are dealing with the flux of entropy, which means that this modified entropy H dot will be a constant. There will be a flux coming from the generation from the external forces. So anyway, if you calculate it, you get a very simple result, which is that it will be equal to omega x plus y divided by 2, omega x minus y divided by 2, multiplied by the alpha of x plus y divided by 2 minus the alpha of x minus y divided by 2. And we take an expectation value. So you see the obvious analogy between this and this, and the fact that as y goes to 0, staying in the inertial range, we must get a constant. Actually, so the index alpha you have d dy alpha here. That's what you get from this integral directly, and you get one of the typical equations one of the classic equations in the theory of turbulence, which was the starting point for Kolmogorov, and which is called Karman-Howard equation. That for I'm doing this for entropy, but it will work for any integral of motion. What? So that's the flux equation, which tells you that certain three-point functions are linearly depend on y, and which actually means that you have a constant flux in the momentum space, because y in a momentum space becomes a derivative with respect to p, and you can actually rewrite b as a flux in the momentum space. I remind you that quantum anomalies in electrodynamics also have interpretation when you have a triangle anomaly. This triangle anomaly actually can be written as a integral in the momentum space of some topological invariant. That's the well-known fact about anomalies. So, and here it's also can be interpreted in this way. There is also another analogy when I discussed E plus E minus annihilation. E plus E minus annihilation, I said that I'm calculating momenta and I'm getting the analog of Karman-Howard equation is the fact that for n equals 1, gamma is equal to 1. It's just a conservation of energy. So there are no fractal dimension, no anomalous dimension for n equals 1, but then otherwise there is. And just to for completeness, of course, you realize that it's not only E plus or minus annihilation, but also if you look at the deep inelastic scattering of electrons, the picture will be the same. So the whole thing displays some similarity. And we have to develop now the, well, we see, we can evaluate naively dimensionality of operators using this Karman-Howard equation. Another equation, to give you the feeling of how they look, another equation for energy, this is the flux of entropy. The flux of energy will be simply and it refers to any integral of motion. Just like with Gibbs, as you remember, any integral of motion just can be added to the Gibbs formula. Here also, this is the analog of constant energy condition in Gibbs case, the flux of energy, which obviously breaks down time in the time reversal symmetry. Now, how we can use it? If we think of naive dimensional analysis, and that was basically the derivation of by Kolmogorov, that you see that V scales like distance. Let me write it here. V scales like for the energy cascade. In two dimensions, this energy cascade is called actually in the inverse cascade, because that will be very important for us, as a matter of fact, for one of the applications. Inverse cascade means the following. Direct cascade, the entropy cascade. For entropy, let's do the estimate for entropy. Can you tell me the answer? Who can? Omega is dV. Yeah, right. Anyway, the inverse cascade, the direct cascade, is propagation from large distances to small distances. The inverse cascade is propagation from small distances to large distances. Why I think it's very important to examine inverse cascades? Because that's what the universe does. It starts with a Planck scale, and then it propagates to macroscopic scale, and this is the natural mechanism for this. Moreover, in a minute we will derive scale invariant spectrum from this thing. So I think it is of some interest. You see, I'm actually moving in several directions simultaneously now. Actually, if you don't interrupt me, it will be even more confusing.
So it's just two-dimensional case, right?
So far, yes, but now I'm going to higher dimensions.
Without inverse
With, yes. That's what we, the possibility which we discussed with Victor Hot. And this possibility, and the possibility based on the following. First of all, this fact that entropy that you have entropy cascade in 2 dimensions. This is a widely known fact, a very well known fact, and which was originally invented. That's a non-trivial fact, actually, that you have this thing, and it was original proposal by Bob Krachnan and Batchelor. No, not Batchelor, or maybe Batchelor, yes. But there is also a much less known situation, which may be of interest, which is based on the work by Zakharov and Yehot, which is the following. You can describe, the Euler equations are Hamiltonian equations. They have well-known Hamiltonian structure, but it is a little bit clumsy. The commutator of 2 velocities, the Poisson brackets of 2 velocities, is actually proportional to the curl of the velocity, so it's not a standard simple Hamiltonian. Well, it is a simple Hamiltonian system, but for quantum theory and for functional integrals, it's inconvenient. It is possible to introduce variables in which the Hamiltonian structure will be standard, and that was done actually in the 19th century. They are called the Clebsch variable. I shall explain what it is. It's an extremely simple thing. Suppose we have a complex function, like complex field in electrodynamics, and we parameterize the velocity in the following way. Now I'm in 3D. We parameterize the velocity in the following way. It's just proportional to the current for those psi fields. Namely, you take psi dagger, you take the derivative, which acts in both directions, psi, and you take a perpendicular projection. Perpendicular projection means, that by definition means that it is non-local, and you have that is needed, this perpendicular projection is needed to satisfy d alpha equal to 0. Of course, you can also introduce auxiliary field to get the same result, but that's good enough. Now, the things are extremely simple now. We actually have the Hamiltonian is simply V alpha square. You have to express V alpha in terms of psi's, and the Lagrangian is just psi dagger psi dot minus psi dagger dot psi with I minus Hamiltonian. So it's very very canonical, and it's you can obtain it by some limiting procedure from the Bose gas. Now, what we were thinking of was that let's try to, well, that's the work of Zakharov and Yehot, who first analyzed it, and let's look at the Karman-Howard equation in the same way. Again, we write it down. We consider now the flux of Clebsch's, not entropy, not velocity, but of Clebsch's. Same thing. well, yeah, of x plus y. What?
So this flux of what is it?
Excuse me?
The flux of what?
Well, that's a good question. I don't know what it is. It looks like something. The Clebsch variables. Let me just finish. So we have the flux of Clebsch variables, which don't have a simple interpretation in terms of the velocity. It's easy, of course, to write down non-local formulas, but
Crudely as the analog of potentials, which define the velocity.
it's an analog of, I would say, of the stream function, yes. But in any case, they're there, and they're meaningful. And what is more, and what can be shown is that first, that they will generate, this cascade is the inverse cascade, like the cascade of entropy, of entropy into energy in 2 dimensions. So there will be inverse cascade here. Moreover, if you calculate the energy spectrum, you will obtain dk divided by k. Contrary to that's the inverse cascade, while the direct cascade is the famous Kolmogorov's formula. Well, it's derived from Kolmogorov. So Kolmogorov index is 5/3, while this one is. So that's a tempting direction, I think. But I will move now to.
So, can you say what you're averaging over?
Oh yeah. Well, you see, we assume that there is a random force. I will actually explain this in a little more details in a moment. This random force causes all quantities to become random. Now, the brackets here and here means the expectation value with the averaging with respect to the random force. So, in quantum field theory interpretation, it's vacuum expectation value. But
I mean, really in that case that you wrote down with Hamiltonian Lagrangian, where's the random force?
Oh, it's left out here. I just random force as well as generating force are assumed to be there, but they are not visible. Well, sorry for a bad joke. Just that. You see, I'm writing down it in the inertial range, and then in the inertial range, which is the only relevant thing for this matter, you don't see random force. Your momenta, you write down things like psi k, psi minus k, and with k less than lambda, and the cutoff. The energy is generated at the cutoff and then propagates through the system. So this is again precisely like axial anomaly in quantum electrodynamics, in which you introduce Pauli, for example, Pauli-Villar's regulators, and you say they break gamma 5, they break axial current conservation, but and that's obvious. What is not obvious and very meaningful, and then there starts the flux through the momentum space to the observed momentum, to the infrared momentum, and this flux is the coefficient. This flux is basically proportional to the coefficient when you have FF dual for the anomaly. The coefficient here, which is the numerical value of triangle diagram, can be written down as a divergence of momentum current. which is sometimes quite useful. That explains, I'm digressing all the time, I'm sorry about that, but cannot stop myself. You see, for me, when there was for some time before this was realized, there was a problem that we have the Adler-Belge-Kiev anomaly equation. There is a certain coefficient in front of FF star. Now, we know that if you have instantons, the left-hand side is an integer. And then by some miracle, this numerical coefficient in front of FF dual turns out to be such that there is no paradox, that the right-hand side of the anomaly equation is also the integer. If these coefficients would be different, there would be a paradox. It would be unclear what instanton is doing. How it happened technically, because instanton is highly non-perturbative phenomenon, while this constant is just the value of triangle diagram. You see, so there is a tension between two statements. And the answer is that it's also topological, but in the momentum space. So coefficients of anomaly, and those coefficients B here are also related to the currents in the momentum space. This is this here is a topological current in the momentum space of the ordinary Feynman diagram. Of course, it's now there's lots of such examples in topological insulators and things like that, where they use Berry phase.
Sasha, can you explain again? In higher dimensions, you say there is another cascade inverse with certain scaling exponents which should compute of some non-local quantity?
Well, which yes, I'm saying there is the cascade, inverse cascade in 3 dimensions, which corresponds to the flux of the basic conserved integral. The flux is of these Clebsch variables, which, as I confessed, I don't really understand physically and don't have an intuitive picture of what the Clebsch variables are. Although the algebra of Clebsch variables is very well known to me, and I don't know many relations and how to get from Bose gas by limiting procedure to this, all that I know, but it doesn't help to understand the simple hydrodynamical meaning of these guys.
Is the forward cascade also present? Is the downward cascade also there?
No, there's the standard direct cascade of N of Kolmogorov. When you have energy cascade, it's standard, of course, but that's a differently excited cascade, which is the inverse.
It is not in the energy density. It is not
no.
Exactly.
No. Okay. Now one more thing. So when we started, it was
11:30.
11:30. Okay. So we are. I still have 45 minutes. Okay.
40 minutes.
40 minutes. Good. I will add, since we have time, I will add a few words about techniques, about trying to, the idea being, of course, to use the richness of quantum field theory, to use it for hydrodynamics. And let me mention to you a couple of things. A good way to start is to use perturbation, to start with perturbation theory. So we have things like that. And there's a force plus pressure, etc. And we can try as a first approximation, and here is new. You see that in linear approximation, we have V is 1 over I omega plus mu k square F, and then, which we can draw as a picture. We have a propagator. This is the propagator, and it ends on F. And we can also calculate in linear approximation VV. What I'm doing now has nothing to do with turbulence, it's laminar phase. But then we will try to resum and see how the turbulence will appear. So the correlation function of 2V will be F square divided by omega square plus mu square k to the fourth. And it was noticed in the 1950s by Wild that you can have a diagram technique here. So we have this as a zero approximation. The next approximation would be the diagram like that. You have the vertex coming from this term, which is of course very easy to extract. So we have linear force, quadratic force, and so on. And as a result, there will be two functions. The correlation function VV, which we'll call F, and the correlation function VF, which we call G. And the diagrams will be more or less, well, at the first glance, it's not clear how they look, what they mean. And there's a very nice way you can check the following fact about the diagrams. So far it's just methodology. It's not no physical results here, just methodology. The fact of this methodology that it coincides, it's the limit of the so-called Keldysh technique for in field theory. In Keldysh technique, that's the technique which replaces, which is extremely useful in condensed matter physics and cosmology and in many other places. You have propagation in time from minus infinity to plus infinity, and from plus infinity to minus infinity, and so you have, as a result, you have the time is double valued, and the green functions there depend not only on space-time point, but also on the Ising-like variable, plus or minus, which tells you whether you are propagating to the future or to the past. You may not know what you are doing, propagating to the future and to the past, but these indices tell you what you are doing really. And then you have usual Feynman rules, but you have also to sum over things. It's not obvious in this form, but that we have we define the green function as a chronological product of some fields. C is this quantum. And as far as the two-point function are concerned, you have the following. You can, by changing some of the basis or something, you can you have the ordinary T product. I'm sure you know all I'm saying, but there will be, if you have patience, in a minute there will be something not completely trivial. Now there is anti-T product, and there is also the anti-commutator, the fluctuator. So when you have when you apply it for if we call this function f, it turns out that it's precisely the function f of the Wild technique, which is obtained here, and the Keldysh technique, which for if you have finite temperature, for example, you will have the T product, this thing, and you will have the analog of this thing will be the retarded commutator. Have retarded commutator. And you have the Matsubara green function which is periodic in imaginary time. I think a good terminology would be to call this thing correlator, this thing natural to call the fluctuator, and this then would be natural to call a Matsubator. That's my small contribution to terminology.
The double field? What is the meaning of the double field?
Of the
You have to double the field.
The meaning is very simple. You want to examine expectation value with respect to initial state. In the Feynman approach, it's quite actually remarkable that in Feynman approach you apparently violate causality, because if the Feynman green function outside the light cone is non-zero. But we know that if the vacuum is preserved, if the vacuum is preserved, then the Feynman green function Feynman technique is not applicable. If it is preserved, then everything is all right. Causality is fine. If it's not, vacuum is changed, like by some particle production or something else, then we are in trouble. We need to use Keldysh approach.
We just calculate in out in Feynman.
What?
If you use Feynman, then we will calculate
in out. Yes, but you will not be able to calculate the observable. Yes, please.
I want to ask you, because you mentioned it, I was always very confused about this kind of statement, because the statement which explicitly mentions something like adiabatic turning on and turning off interaction.
Yes.
Actually say something about vacuum being changed at all. Whereas usually in quantum field theory there is a derivation of the entire dichromatics where you never turn off the interaction, right? You don't.
Well, you do actually. You see, if you have Feynman propagator plus I epsilon, and this I epsilon is actually adiabatic turning off the interaction. You can always interpret this Feynman propagator as you start with certain vacuum, then it develops, and then you adiabatically you turn on without this turning on and off the interaction. There will be no consistency. So it is very important that I will tell you the. Actually, that relates to what I wanted to say. So that's the Feynman propagator. But if you look at the general vacuum, the propagator for the free field will contain the distribution function. There will be the expression like that. Now, see what happens. What will happen if you naively assume that there is no moving back to the past? In Feynman, you move from the past to the future, and in Keldysh case, you move back. If you don't move back, You have two terms here, and you calculate some diagram like that. And you have to put this propagator here and here. Now you are in big trouble because you have poles. The poles pinch the real axis. You will have the term like p square minus m square plus epsilon square, which is delta function of 0. So there will be some meaningless divergences. I shall explain in a second what they mean, but apparently they're meaningless. Naively they're meaningless. Proportional to delta of 0 with this type of propagators. What happened? It means that we don't have the steady state. It means that the system depends on time passed from the beginning. You have the beginning long ago, and then the contribution of perturbation theory will contain this global time. What does that mean? It means that there are interesting consistency conditions. You have to write down the Boltzmann equation. And if f if this collision integral is non-zero, then f under iteration will contain terms proportional to t. And that's precisely the term you discover by looking at the Feynman diagram with this propagator. So what I'm and so consistent backgrounds must, steady state backgrounds must contain this thing. And then you can ask, we know, it seems that the only such background is Bose or Boltzmann distribution functions. In turbulence, so I of f is something like, if you have, for example, the scattering like that, you have the integral matrix element square, terms like f, 1 plus f, 1 plus f, and so on. That you can derive from diagrams. That's the Boltzmann collision integral. And now I'm coming to the known fact, but which is not very widely known, that the condition that this integral is 0, of course, has the solution, the standard solution of Bose or Fermi distribution, but it also has turbulent distribution. It also has distribution which were discovered by Zakharov in the 60s, in which f is scale invariant. It's actually Kolmogorov-like, and it nullifies the collision integral, so the system becomes stable. So the basic point which I'm trying to make is that Keldysh technique actually predicts to some extent or restricts the possible distribution function in the steady state, and among these, and it describes not only thermal distributions but also turbulent distribution, and that can be derived very simply in just a few lines, but I will probably move on. Yeah. What?
Everybody may be aware, but I was a bit lost. You start with earlier reflection, so you can.
With what? With
earlier.
Then yes.
You consider this nonlinear term at the beginning developing perturbation theory.
Yes.
Then now you changed background, perhaps, and I don't know. You were doing also perturbation theory in terms of diagrams without even having perhaps small coupling constant.
No. Right. What I derived here refers not to, you are completely right. It's my fault. I should have formulated more clearly what I'm doing. You see, it refers to the system with weak interaction, not the Navier-Stokes equation. Imagine, for example, you take the Navier-Stokes with small coupling constant. You put some. It's not a very good idea, but in any case, so it's there are systems like weak turbulence, theories of weak turbulence, in which you have coupling constant. So this collision integral consideration refers to this system. It's only for weak coupling. But what I was trying to say, and what is important, is that for weak or strong coupling, Kelder's diagram contain the turbulent solution, turbulent distribution.
Because there is deviation from some kind of vacuum, you mean there are occupation numbers, there are collision integrals, and then you mean that in this case you have this kind of collision terms.
Yeah, collision terms. But I'm saying yes, but I'm saying actually it's quite spectacular result that we all know that collision integral is zero for thermal distribution, but that it has also another solution. It's terrible for Kolmogorov solution. It's highly non-trivial.
But are you saying also that in strong turbulence, fully developed turbulence, still a probability distribution function should satisfy collision integral equal to zero?
Yes. Or generalized collision. Collision integral is perturbative thing. Collision integral by itself is.
What's the definition of the condition?
Okay. The definition is there, and it's extremely simple. It is just that the green function it's a steady state condition. You can derive, I can show, I will not do this because...
And how people missed it at the beginning, that there is the other solution, not just sigma?
Well, that was, as I said, discovered in the 60s by Zakharov, yes. It's not directly applicable to turbulence for the reason you just mentioned, that turbulence is a strong coupling from the very beginning. But nevertheless, it's very important. And I have actually, if someone is interested, I don't have time to go into this further, but I will be glad to show two-line derivation of this result. Okay. Now I'm coming to something which to some new things. I try to look at the following. In statistical mechanics, we know that we know what it means. The statement like Ising model is equal to phi-4 theory. Okay, what does that mean? It means the following. We have the equations, the equation of motion in phi-4 theory, classical equation of motion. And we can actually find the field theory solution. Especially, it works nice, especially explicitly in the conformal field theory. In conformal field theory, we know various operator product expansion. And what I'm saying is that the equations one should read them in a Hebrew way, from the right to the left. Actually, I can tell you, to get some rest from these confusions, in 1970, I wrote a short review of CFT in which I mentioned this fact that it should be you should read it in Hebrew. And that was then in the middle of the night, the editor called me almost hysterical and said, "Are you crazy?" I said, "What? You are saying, you are mentioning Israel. You are referring to our enemies." I said, and I actually answered very, very diplomatically, but it didn't help though. I said, "But look, we use American terms all the time, and they are also our enemy." It didn't help, so it was cut out. Actually, it was some strange thing happened. There was a preprint where it was removed, and then they planned to publish a book of, it was some conference, and the book never appeared. But anyway, but the preprint exists. So, reading it in this way, you should be saying the following. Let's do the point splitting again. So you have phi x plus epsilon 1, phi x plus epsilon 2, phi x plus epsilon 3, and the OPE, generally speaking, will contain a Laplacian of phi plus b some other operators and so on. That's for general CFT. But what about the right CFT, which describes the Ising model? Very simple. It must not contain these terms. So the only CFT which does the job, which the OPE of which in the leading order is just the Laplacian of phi, is the minimal model corresponding to the Ising model. So the idea, natural idea, so that's the way you solve quantum differential equation with OPE, with operator product expansion. It's tempting to try this in turbulence, and the results, so you can, the problem arises then that there are too many solutions and it's not clear how to select the right solution. You have to impose, first of all, the Euler equation on the OPE. The OPE should reproduce the Euler equation, that's one condition. And the other condition, it should reproduce the constant flux relation. And in general, the answer is, well, you can do something with this, but not very much. You still, there is still huge a problem. I will tell you how it goes. I'm now coming to really unresolved problems. And then I will make a conjecture which is testable. But again, it's testable, but I don't know if it's correct. One of the way of doing things is to notice that the velocity is incompressible. So in 2 dimensions, one introduces the so-called stream function. I use the same letter as for the Clebsch variable, although they are strictly speaking different, but they are related. In a sense, I think stream function is dimensional reduction of the Clebsch variables are valid in 3 dimensions, while the stream function is in 2. Then the vorticity is what is vorticity is the Laplacian of the stream function. And the equations of motion is just this. And again, it's, I'm not writing, I'm not presenting here the forcing term and the dissipation term. We are supposed to be in the inertial range at the moment.
Are you considering the direct cascade now? Or
The what?
the direct cascade or the inverse?
Actually, both. I will be talking about both things. Well, you see, we have the equation. If we the steady state equation would be something like epsilon alpha beta d alpha psi d beta d beta d square psi is equal to 0. That's the classical equations which we want to solve with conformal field theory. The general strategy is always to, I'm not completely certain it's working, but at least the best we can do is to try to find a conformal field theory which satisfies this thing. Now the question is how to deal with it. What I tried to do, and which I will change now, the simplest step would be to assume that psi is a primary operator of CFT. And then the question is, what is this expression? How to find, it's kind of a, we want to find kind of a correspondence principle, how to translate classical equations into quantum field theories or solve these equations. The question is what it is. And there's, if we suppose that we have some psi is a primary operator, you have psi multiplied by psi, which could be some operator phi. Then if this operator product, if this fusion rule is given, then how to get the analog of this equation. And the analog is, turns out to be that is the following. We have it cannot be a primary operator because, well, there are no primaries of this type. And in this simple case, it must be time reversal non-invariant. And the only expression one can write is this one. And then you have you can use this for writing the steady state condition, the constant flux condition, and so on. So that's the simplest operator with proper quantum, with proper symmetries, with proper quantum number. But it leads to a somewhat unpleasant feature of the theory, which basically forced me to drop this, to change the subject. This is when I started understanding it. You see, we are, how shall I put it? The unpleasant feature is that we have this expression equal to 0. So, and since psi is the primary operator, we assume so, it means that the correlation function of 3 vorticity is 0. Let me explain this. That's a crucial point, and that's really crucial for the new result I'm going to display. So let's start again. When we have a primary operator, the correlation function of 3 of them has the form x12, x13, x23 to the delta, and as you see, it contains no epsilon tensor. It is impossible for the scalar primary to break parity, you see. Which leads to immediate conclusion that the 3-point function and vorticity breaks parity. Vorticity operator is which leads to the conclusion which I now don't believe, namely that correlation function of 3 vorticity is 0. Well, and as I said, what plagued the theory was the ambiguities of.
But this is only 2-dimensional.
2-dimensional, yes. Yeah, even 2-dimensional would be nice to understand.
Are you referring to which data that the 3-point function?
What?
Which data convinces you that the 3-point function of the vorticity is non-zero?
Well, you know, it's not so much the data, but some consideration of the flux. The flux is non-zero, and I think so. That's an interesting thing, that when you have this equation, when you look at this equation, you see that the 3-point function is non-zero. But you can argue that this correlation function, it's a bit difficult to explain that, but the correlation function is analytic in Y. At the same time, if you take, let's look at the correlation function omega of x1, omega of x2, via alpha of x3, from which you can obtain this function. This function, when this point, when x3 coincide with either x1 or x2, this function should give a non-zero result. So the structure of this function is highly non-trivial. Namely, generally speaking, it should be some transcendental function, some function containing powers of x1, 2, x1, 3, etc., which becomes a polynomial when 2 points coincide. And I actually played around with this function, and it seems to me now that it's impossible to fully satisfy the steady state condition if the dimensionality of this thing is not, if we have only, you can say that this function, it's a bit difficult to explain. So the basic point is, let's study the properties of this function. It is restricted by incompressibility condition. And so you can write down the general ansatz. Now you demand from this general ansatz that it becomes steady state, that it is linear at by alpha. And my impression now is that it is impossible to satisfy if this function if the 3-point function of vorticity is 0. So in any case, let me suppose that it is not 0. and write down the expression for this 3-point function. In fact, that's I said at the beginning that there will be a new conjecture at the end, and that now I'm going to formulate this conjecture. It may be right or wrong, but it's very concrete and very testable. So, in order to explain the motivation of this conjecture, let's return for one moment once again to the Ising model. In the Ising model, we have physical quantities like spin, energy, and so on. They are not precisely conformal operators. We used to say that these are conformal primaries in the minimal model, which is correct, of course, but it's not precise. In fact, we say that epsilon operator is epsilon CFT plus higher corrections in cutoff. There is an ultraviolet cutoff multiplied by some other operator. They are just irrelevant as we go to the infrared limit. When we take the lattice to 0, when we go to the critical point, these operators are small. But generally, all primary operators are linear combination of all possible operators by symmetry. It's just that some of them drop out, some of them are irrelevant. In this sense, let's assume that omega or psi is such primary operator that it cannot have the term which is independent, which is a conformal primary. It cannot be conformal primary. But what is the minimal expression which it can be? The minimal expression is once again this. Multiplied by some primary phi. This time the 3-point function will be parity will break parity, so that this 3-point function will contain epsilon tensor, because epsilon parity here is just changing things to complex conjugate. And this time you can calculate, if you make this is the first term plus higher terms which are smaller in the same sense, like that. So we are just saying we cannot have here anything lower than that, any field phi, because it doesn't break symmetry. That's the minimal operator which breaks time reversal invariance. So let's try it and see what we can predict from this. This time we can calculate omega, omega, omega. And it's a pretty terrible calculation which can be simplified, because you have to use word identity, the product of three things, you use word identities for them and so on. Things simplify a little bit if you actually introduce the operator 3, 2, 2 delta plus 1, L minus 1 square, and complex conjugate instead, because this term will cancel anyway, but this is projectively invariant. It's quasi-primary operator. In any case, to make a long story short, well, that simplifies things a lot, but it's still very complicated. And my secret weapon was my student, who loves to make difficult calculations, Grisha Ternopolsky. And he wrote the answer, which I decided to make a copy of it, but I couldn't finish, so I shall write down just the beginning of the answer. So just to get you the feeling of what goes on, of what kind of, and we will compare it with something which is also known.
So are we writing it in conformal figure or in turbulence?
We assume, okay, fair question. We assume that the two-dimensional turbulence is conformal. Let's assume this. And that's what we will be testing, as a matter of fact. So let's assume it is conformal. And let's assume that the three-point function of artistic is non-zero, which I think I will find some good argument for this.
Weren't there papers by Falkovich and others saying that it is not in fact conformally invariant, the correlation functions?
There are, of course, you are referring to direct cascade now. Well, there is no proof that it is not conformally invariant in my view, but in any case, I'm talking now about inverse cascade, in which case we certainly have not. You see, the problem with direct cascade, there are logarithms which can indeed spoil conformal invariance because of this proportionality velocity to r. It involves, the correlation function involves a lot of log. It's in fact not r but r log r, and so indeed it's possible that it is broken in direct cascade. There is no such thing in the inverse cascade.
This last paper on the OPE.
No, I will refer to the. You are referring to Zamolodchikov paper, and I'm going to compare this paper with it. And what I was saying before your question referred to the very old story, very old paper, and that's. But now I will write the answer and then compare it with. Zamolodchikov paper. So we have the answer for all three things, and just to show you the level of difficulty, it is for the model with central charge C is 441 C minus what is it?
Yes.
That's why Kolmogorov is so much better.
It is. It is Kolmogorov. This formula, which I'm writing down, is obtained under assumption that Kolmogorov works. But Kolmogorov says nothing about three-point functions. I will stop in a second. So there is a configuration like that. And this is a long equation like that. And now there was as you already mentioned, there was a relatively recent paper by Falkovich and Zamolodchikov, who analyzed in general dimensions. They analyzed operator product expansion. They did not assume conformal invariance, but they just looked at the operator product expansion. Turns out that our formula become very close to theirs. You can extract what they calculated was not the full three-point function like here. It's the answer for the all points in arbitrary position. They, using operator product expansion, calculated the things which, when two points come close together. That's precisely the situation for the fusion rules. And they derived it under assumption of a certain structure of operator product expansion. Now, turns out that then this term is 0. We are very close to their answer. The structures look very similar, and I believe that in 2 dimensions conformal invariance has some extra terms in the operator product expansion, and that causes the difference between their results and ours. But that's still to be thinking about. One must think about it. In any case, there is something to do here. There's some game to play. Okay, and
is your conclusion then that even in the inverse cascade there is no conformal invariant?
no, not at all. Quite the contrary.
I saw the 3-point function of the vorticity being non-zero is in.
No. What I'm I was bad explaining. Explained it very badly. What I'm saying is that let's assume that there is conformal invariance. What about, and let's assume that the 3-point function is non-zero, for which I will give later some arguments. Then the vorticity cannot be a primary operator. It's a descendant operator, and the lowest descendant operator generates is the one which I just erased. And so using this fact, we can calculate in a most explicit way the 3-point function of vorticities. And then compare. The next step would be to compare it with the data, with other assumptions and so on, but that's not.
Do you assume anything about unitarity of the CFT?
Well, I think that there are the CFTs describing turbulence must not be unitary. They cannot and must not be unitary because you need negative dimensions, and there's a random force like that. It doesn't generate unitary field theory. But we have a lot of interesting non-unitary CFT, which actually another interesting point, not related to turbulence. I guess that this non-unitary CFT describe vacuum decay. You see, what I'm referring to is that there are nice non-unitary CFT with beautiful OPE and so on. It's known in the Euclidean domain that they describe statistical system like percolation and things like that. The question is what they describe. That's another question to think of. What they describe in the Minkowski domain. And my conjecture is that they describe vacuum decay. You start, they introduce negative probabilities. And negative probabilities means that the floor gives way under you.
Can I ask a question? So I thought in the past people found isovorticity lines in 2D inverse cascade.
Yes.
That correspond to particular field theories with a certain central charge.
Yeah.
So wouldn't it give you, if you assume that there is
good question, and we certainly will be thinking about it, but I don't know. But it's make perfect sense to compare it with these older results on. So I think I could continue another 2 hours if you like.
Then will be fired as chair. Then Caesar experiment will be fired.
as a chair, not fine.
As a chair.
Okay, then. Okay, thank you very much.